In this video, we're going to be talking about periodic table trends, and the first trend we're going to discuss is atomic radius. Atomic radius, if you're unfamiliar with what a radius is, it's really just it's the distance between the center of a circle and the outside. So if you had a circle, it's the distance from the center to the outside. So in context of chemistry, in an atom, it's going to be the distance from the nucleus to the outermost, to the valence shell. But just think of it as the size. So think of it as the size of the atom, the overall size, and you're going to be just fine. So atomic radius, the trend that we have going on here, I'm going to draw a couple of examples and let's think about them. So if I were to ask which atom has a greater atomic radius between hydrogen and potassium. Pause the video for a second and think about it. Maybe drawing a Bohr model might really help with deciding which one has a greater radius. Draw your Bohr model and then come back and decide which one has the greater atomic radius. So if we were to draw a Bohr model for hydrogen and potassium, for hydrogen we're just going to have one proton in the center, and then we are going to have one electron around it. For potassium, our Bohr model, we're going to have a total of 19 protons in the center, and then we're going to have 2 electrons on the first shell, 8 electrons on the second shell, and then 8 electrons on the third shell, and we will have 1 electron in the outermost valence shell. All right, so just looking at between these two different atoms, go ahead and think about which one looks bigger. The one with the radius, one has a radius of only that big. The other has a radius of that big. And if you don't care about what a radius is, that's fine. Which one looks bigger? And I would say that potassium definitely looks a lot bigger than hydrogen because it is bigger. And it's bigger because it has more electron shells, so more energy levels. The greater the number of energy levels, the greater the radius. You might also think, okay, well, potassium, if it has 19 protons and however many neutrons, it has a bigger nucleus as well. But let's look at that. Let's look at our nucleus here. And so I've got this nucleus here, right? And it's definitely bigger inside of potassium. But let's look at how big the nucleus is compared to the rest of the atom. I've got this whole atom here, and then this tiny nucleus in the center. But the nucleus only makes up a really small part of the atom. So even though the nucleus is bigger in potassium, that's not because it is what's the driving reason for why the atom is bigger. So yes, potassium does have a bigger nucleus than hydrogen, but that's not why it's a bigger atom. It's a bigger atom because the electron shells, it has more electron shells, and that's really the main factor that makes it bigger. So don't get that confused. Let's try another example. What about what if I have let's do cesium here. What does that one look like? And is that going to be bigger than hydrogen? Is it going to be bigger than potassium? Let's think about it. So cesium, we've got our protons and neutrons, and maybe it's a slightly bigger nucleus because it has 55 total protons. But that's not really much of a concern. So it's going to have its first energy level, second energy level, third, fourth, fifth, and then it'll even have a sixth energy level. And we won't worry about how many electrons go inside of each shell, but I actually was able to look at the periodic table and determine how many energy levels it has without calculating how many electrons go in each shell. So think about how I was able to do that. It's something I pointed out in some other videos, but maybe we might have forgotten it. Let's look at a trend that we have going on here. Hydrogen is located in the first row of the periodic table, and we said it has 1 electron shell. And then potassium, it's located in the 2, 3, 4th row of the periodic table, and it has 4 electron shells. So cesium, it is located on the 6th row of the periodic table, and it has Cs has 6 electron shells. So the trend, if we fill in the rest, we could find that the row number is going to actually tell us the number of electron shells. And the greater the number of electron shells, the greater the radius. So our first trend with atomic radius is that as we go down on the periodic table, the radius increases. So the further we go down, the bigger the atom. But what about when we go left to right? What happens then? Let's think about that. So I'm going to erase my example with cesium here. And then let's keep in mind that that the row number on the periodic table tells us the number of electron shells. That's going to be another important trend. All right, but as we go left to right, what happens? Let's figure that out. So let's do these two examples, lithium and neon. So let's try that out. Lithium, Li, and neon. So lithium, we're going to have 3 protons in the nucleus, and then we're going to have our first energy level, and then we're going to have our second energy level. All right. Whereas neon, if you want to draw a Bohr model for neon, we know that there are 10 protons. And by the way, this isn't like a full Bohr model. Don't think that this is how we're drawing Bohr models from now on. I'm just drawing it very quickly so we can get the point. But a true Bohr model is going to have protons and neutron numbers and then electron numbers as well. But just drawing a very rough sketch, neon has 10 protons in the center, and then it's going to have the first energy level and the second energy level. And it's going to look like that. And we know that it only has 2 energy levels. Both lithium and neon only have 2 energy levels because they are both located on the second row of the periodic table. Second row is going to mean 2 energy levels. But why did I draw lithium with the energy levels very spaced apart? Whereas neon, they're pretty close to the nucleus. Why did I do that? Well, let's think about it. If I have, for lithium, I only have 3, remember I only have 3 protons in the nucleus. But for neon, I have 10 protons in the nucleus. So think about we know that protons and electrons, they attract one another. They're oppositely charged, so they attract. And protons and electrons attract each other, and if I have more protons, that means I can create a stronger attraction. So a stronger pull on those electrons to pull them in closer. So since neon has more protons, think of it as having a stronger magnet to pull the electrons in closer. So they want to get closer to that very strong magnet inside of neon. Whereas lithium, it only has 3 protons. So it has a very weak magnet. The electrons aren't just going to drift off into space, but they're not as tightly bound to the nucleus as they are in neon. So think of the nucleus as like a magnet where we have like positive end of the magnet, or north pole, and then the south pole is going to be the electrons. And when we have a weak magnet, it doesn't have as strong of an attraction, so the electrons are going to be further apart. But when we have a strong magnet, it's going to pull those electrons in real close, and that's what happens with neon here. So let's talk about another one. What if I have sodium what about if I have, let's just do something on the same row. What about boron? All right, so if I draw boron, and I'm going to have a total of 5 protons, and then we're going to have our 2 shells. And it's not, so this nucleus inside of here, we have 5 protons. So it's a little bit stronger of a magnet than lithium, but it's not as strong as neon. Neon has twice as many protons as boron. So boron is going to be smaller than lithium, but bigger than neon. So so go ahead and take a second, pause the video, and think about what the trend might be for atomic radius as we go from left to right on the periodic table. All right, so if we notice, we have, let's list these in order of size. So the biggest one is neon. Then we have the second biggest in our 3 examples here. First biggest is lithium. Second biggest is boron. And then the smallest is going to be neon. So if we picked up on the trend is going to be the greater, the further we go to the left, the greater the atomic radius. So let's erase these 2 arrows and draw them condensed into one and figure out what that is going to look like. So the overall trend for atomic radius is going to be, as we go down and to the left, the atomic radius will increase. So the biggest element that we have is going to be francium, because it's the furthest down and to the left. And then the smallest atom that we're going to have is going to be helium. All right, so hopefully that was helpful describing atomic radius, a very important trend with the periodic table. We're going to be discussing more trends in future videos. The periodic table is arranged in such a way that there are lots of trends that tell us, that allow us to predict a lot about elements just by looking at where they're at on the periodic table. So hopefully that was helpful. I'll see you next time.